Hello students, in this video we are going to discuss about a ray optics numerical, so mainly which is based on this lens maker's formula. Let me read the problem first. Two identical thin plano convex lenses. See here, these are the two thin plano convex lenses of refractive index is given, which is 1.5, and each having radius of curvature is also given, which is 20 centimeter, are placed with their convex surfaces in contact at the center. So which means lenses are in contact. The intervening space is filled with the oil of refractive index 1.7. See here, the air gap usually between these two plano convex lenses, this portion is covered by air, but now we are covering it with the oil having a refractive index of 1.7. So this portion, this gap, the entire gap is covered with the oil having refractive index 1.7. So now what happens? So this gap portion acts like a concave lens. See, this is a plano convex lens. This is 1. So let me take this as f1, the focal length. So the intervening space is going to act as a concave lens, and the third one, which is f3. Okay, the question is the focal length of the combination. So we know the formula for focal length of the combination when lenses are in contact, which you know very well. So 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3, which is very easy. The oil is not there, it is only two lenses, f1 and f2. Because the oil is filled here, so it means we are introducing, as if we are introducing another lens. So we have to consider the focal length of the three portions. Okay, now for finding the focal length, we have the lens maker's formula. So this is the actual lens maker's formula. So anyhow, the first medium is air here in this case. So mu1 is equal to air. Mu1 is air. So the refractive index, which is equal to 1. So I can rearrange this formula. 1 by f is equal to mu minus 1 into 1 by r1 minus 1 by r2. So now what you have to do is, so separately for the first lens, you have to apply this formula. Similarly, then for the second lens, you have to again apply. And for the third one, you need not apply because it's the same configuration. So you can simply write. So let us find the focal length for the first lens, f1. So I have written the formula. So 1 by f1, I know the mu value, which is 1.5. So 1.5 minus 1 and 1 by r1. See, the first portion is plane. So the radius of curvature will be infinity. So 1 by infinity minus 1 by, and the radius of curvature is given, which is 20, but the radius of curvature falls on the negative side, so minus 20. So 1.5 minus 1 is 0.5, 0.5 into 1 by 20, which is 1 by f1. So 1 by f1 is equal to, so 1 by 40. So f1 is equal to 40 centimeter. So now I have found the second lens. So 1 by f2 is equal to mu minus 1. So here mu is 1.7 for this portion, for the concave portion. 1.7. 1.7 minus 1 into 1 by r1. So the first radius of curvature will be negative because falls this side. So minus 20 minus 1 by r2, that is plus. So it is simple maths. So 0.7 into minus 2 by 20, I can write minus 0.7 by 10. So taking reciprocal, so f2 will be minus 100 by 7 centimeters. So this is the focal length of this the portion, concave portion. F3 already I can put the same 40 centimeters. So now I know f1, f2, f3. Just put it in the formula. See, I have written the formula here for thin lenses in contact, and I have written the focal length values also. Just substitute these values in this equation, you will get the final answer. See, I have done the substitution here. So this minus, so 2 by 40 minus 7 by 100. I have taken the LCM, 5 minus 7, so minus 2 by 100, which is 1 by f. So f will be equal to minus 100 by 2, so which is equal to minus 50 centimeters. So f equivalent will be minus 50 centimeters. So this is the answer, and this answer will be there in some of the option, so you have to choose that option. So the equivalent focal length of this combination, there's three lenses, two plano convex lens and one that in between portion considered as a concave lens. The equivalent focal length is minus 50 centimeter. So students, don't forget to subscribe this channel, and share this video also to your friends, so that let them also be benefited. Very similar to the previous problem, we have another problem here. So which says two similar thin equiconvex lenses. So these are the two equiconvex lenses having same focal length. So both are having focal length f. So this is also f, this is also f, such that the focal length of the combination is f1. The combination, this combination having a focal length of capital F1. Now the second case is when the space between the two lenses is filled with glycerine. So this portion, this space, so space in between, they are going to fill it with glycerine, that is also having the same refractive index 1.5, and this time the equivalent focal length is f2, and they are asking the ratio of f1 and f2. So this space, so again this space will act like a concave lens, but here the refractive index is same, which is 1.5. So focal length of this concave lens portion also will be f, but only it will be negative, because we know very well the focal length of the concave lens is negative, but in magnitude wise it will be same. So we know the formula thin lenses in contact. So let's write the formula for the first case. So where this glycerin is not there, so don't consider this. So 1 by, that is f1, 1 by f1 is equal to, so 1 by f plus 1 by f, so which is 2 by f. So f1 is equal to f by 2. So this is the value of f1. Now coming to the second case. Second case, so 1 by f2, they have given f2, so 1 by f minus 1 by f, because this concave portion, so it's negative, then again plus 1 by f, so two things will get cancelled, so 1 by f. So f2 is coming, f2 is coming, f2 is becoming equal to f. So that's it. So now I know f1, I know f2. So f by 2, they are asking the ratio. So f by 2, and this is f. So f1 is to f2 will be f by 2 is to f. So f gets cancelled. So 1 by 2 is to 1. So I can write it as 1 is to 2. So the ratio is 1 is to 2. The ratio of f1 and f2 is 1 is to 2. So that's the answer. That answer will be there in one option, so you can easily choose.